All right, I see there's still a few people coming in, but in the interests of having enough time for everything, I think it's about time to get started. Um, so welcome everyone to the first Physical Society Colloquium for 2022. Before we get started, I just want to remind everyone who's entered recently that the session's being recorded. And I also want to remind everyone that we'll have an extended Q&A session at the end. And since we have a very large audience, I would ask that you hold onto your questions through the talk, save them for the Q&A at the end. So to kick off the colloquium series this year, I'm extremely pleased to be able to introduce Professor Carl Wieman. Professor Wieman has had an illustrious career in atomic physics and laser spectroscopy, spending much of his career at the University of Colorado Boulder and Gila, where his contributions spurred a revolution in atomic physics, enabled by cooling atomic gases to ultra-cold temperatures. The awards he received for this work are too numerous to list here, so I'll just mention the most notable: the Nobel Prize in Physics in 2001, which he shared with Eric Cornell and Wolfgang Ketterle for the achievement of Bose-Einstein condensation in dilute gases of alkali atoms, and for early fundamental studies of the properties of the condensates. But Professor Wieman is not here to talk about atomic physics today. In the same year that he won the Nobel Prize, he received the National Science Foundation's Distinguished Teaching Scholar Award, recognizing a long-standing excellence and interest in teaching that led to a remarkable second phase of his career in physics education research. At the University of Colorado, he established a science education initiative in 2006. And as a side note, I have personally benefited quite greatly from the Physics Education Technology Project, or PhET project, that he founded there in 2002, which, if you haven't checked it out yet, I would highly recommend the interactive simulations and surrounding pedagogical content. Regardless, in addition to the Science Education Initiative at the University of Colorado, in 2007, he moved to UBC, where he directed the Carl Wieman Science Education Initiative until 2010, and then served for 2 years in the Obama administration as the Associate Director for Science in the White House Office of Science and Technology Policy. Since 2013, he's held the post of professor at Stanford in both the physics department and the Graduate School of Education. As with his achievements in atomic physics, the recognitions for his work in physics education are also too numerous to list, including the Oersted Medal and AAPT Fellowship Award from the American Association of Physics Teachers, and the Presidential Citation for Lifetime Achievement from the National Science Teachers Association. He also founded and was the first chair of the Board on Science Education for the National Academy of Sciences. So I'm sure at this point you would all much rather hear what he has to say than to listen to me anymore. So without any further ado, let me introduce Professor Carl Wieman, who will be talking to us today about taking a scientific approach to physics education.
Okay, well, thank you. It's a pleasure to be speaking to you. So let's see, I've got my screen sharing working. So I'm going to be talking to you about thinking about education in a different way, much more like we do physics. And so I'll generally give a broad introduction about some basic things about principles about how the brain learns complex thinking. And then I'll focus down more onto doing studies in university classrooms about trying different ways of teaching, getting research data and getting principles out of that. And then I'll spend the last part of my talk really focusing down more details about looking at a sort of detailed findings from classroom research about showing how to improve learning in the teaching of physics and why they work. And so these are really, things you can use in your own teaching. And I just want to emphasize that many of you may have heard about different sort of innovative research-based teaching practices or things, active learning and so on. But what's not usually covered, and I think is quite important, and I'll try and do more in this talk, is really get at the underlying principles about understanding not just how to do something, but how and why it works, like we think about physics in the same way, because it really helps one be more effective in applying these ideas. Now, for the audience and the teachers in the audience, it's really a lot of things that research tells you about how you can maximize student learning. But I'm assuming there's some students in the audience, and I think, although I'm mostly sort of targeting teachers, you should really think about these are ideas of just how you as a student can maximize your learning, and really, because ultimately the learning takes place because of what happens in your brain. And for many of these things, a good teacher may help, but they're often not essential. And so you should really think about, how can I apply these in my own thinking? Now, before I get into the details of this, though, I'm going to give you a little bit of background about how I got into education and what my focus of this work has been. And it really came about not because of my teaching in the classroom. It's actually working in my physics research program. And I saw something that really was a puzzle to me, which is that these new graduate students, they would come in to work in my research group after many years of great success in math and science, and particularly in their physics classes. And yet they really were pretty much clueless about how to actually do physics when confronted with the research. But it clearly wasn't anything fundamental, deficiency of them, because after a couple years working in the research lab, they had turned into expert physicists. Now, the first few times I saw this, I thought it was just some peculiarity of the individual, but then I saw it happening as my career went on, a very consistent way. And so I came to the conclusion there's a fundamental question here. And so 30 or 35 years ago, I decided, okay, there's a science question here I want to understand. And so I tackled it just like I would any other science question of, in this case, looking at what the research was on how people learn, particularly how they learn physics. And there was enough out there at that time that it explained the puzzle. It actually made sense. It made me realize there were much more effective ways to teach than what were being used. But it also got me started on doing science education research, focusing initially on physics, but now I've kind of expanded across science and engineering, doing experiments, getting data, and trying to derive from those basic principles. But all the time in this work I've been doing is really kind of with the original focus of really focusing on expertise. What does it mean to be a good physicist? What's the thinking involved, and how is that learned? And so everything I'm going to talk about is really targeted towards that idea of expertise in physics. Now, over the past couple of decades, there's actually been new insights on how to learn and teach this kind of complex thinking of being a physicist. And we're getting complementary results out of brain research, cognitive psychology that really looks at the fundamentals of how people think and learn, and then the research, like much of what I do, of working in experiments in university physics and other science classrooms, trying things out and getting results from them. And today I'm really going to be focusing on these two areas, particularly the connections between the fundamental thinking ideas and how those relate to why understanding what to do and why it works in classrooms. Now, before I really get into any of the details here, I'm just going to give you the very big picture of how this kind of research has really changed how our thinking about how learning happens, at least at the kind of university level. And the old model, which is still pervasive among our higher education, is that we've got these different student brains. They come into our classrooms and they vary in different ways. We immerse them in knowledge, and that knowledge soaks into different amounts depending on what that brain was like. Now, if this is the one's model for learning, this, is underlies why the main focus at universities and, certainly many departmental discussions and so on about education tend to be focusing on, okay, how do we select the brains that are best for soaking up this knowledge, and what do we put in the knowledge soup? That's the curriculum and courses and topics that's going to be most effective. So that's how most really higher ed dominates the thinking in higher education. But I want to say that's just fundamentally wrong. We now know that. What the research really actually shows is these brains aren't very different, certainly at the university level when they start out in the classroom, and they're actually transformed through the educational process. And what I mean by that is actually change the neuron through the intense thinking. And it's really this rewired brain with different neurons hooked up in different ways. It has improved capabilities. And we can actually, researchers can actually see this in terms of looking at brains as they're becoming more expert, and how the expert brain basically lights up in functional MRI images in a very different way than a brain of a novice who's doing the same task. And so what this really says is that, okay, what we need to do in learning to be effective is we really have to figure out how to enhance the right kind of neuron connections, the relevant connections, and that doing that is really very much like, very similar to developing a muscle. You have to, if you want to build up a muscle, you've got to use that muscle, and you've got to exercise it strenuously over a long period of time, and basically it gets better. And what we see is the brain has the same basic features, except now you have to give it the right kind of mental exercise, and it's got to be done intensely over a long period of time. And most importantly is really the brain only learns really what it practices. And so if you wanted to think about how it's going to think about doing physics in the right way, you have to have it practicing thinking, doing that physics. And in fact, researchers across a whole variety of areas are really continually learning more effective ways to teach, to help the brain more quickly and effectively develop new skills. And that, as a good teacher, you really need to be aware and thinking about this. And the most dramatic example I like to give of this is that is the idea of perfect pitch. And for centuries, this was thought to be some extraordinary natural talent that just a tiny fraction of the population had. And in fact, in recent years, as people studied this, now we know, and people have demonstrated, that you can basically teach pretty much any child to have perfect pitch just by the right teaching activities. Okay, so now I'm going to move on to getting more focused on university classrooms and some of the studies done in that. And so there have been many studies done across different sciences, in physics in particular. And those of you not familiar with this, I'll just give a broad picture of it. The idea is, first they figure out some test that's really going to probe how well the students are learning to make decisions in a relevant context, like an expert in that subject, like a physicist would, and in a context that a student has the information to or the access to actually answer those. And then once you have a test that's going to probe that, then you try out different teaching methods and compare them. And so most of the work is looking at in the standard lecture situation, seeing how what students can do, who've been taught that way, and then the experimental comparison is having the students make decisions in particular scenarios where they get feedback on those decisions. And these, broadly speaking, are lumped into what sometimes you may have heard called active learning or research-based teaching or active engagement. So I'm just going to give you an example of one such experiment. It's one I was involved with. And this was teaching the giant introductory physics class at University UBC. And so we were able to take two of these large sections that we could do a whole bunch of measures that's essentially identical students in them. And the control section was taught by a highly experienced professor who had good student ratings, who used a fairly standard or quite standard lecture approach. And the experimental section was then taught by Louis Delorier, who was a fairly new PhD, but had been trained in the program I ran at UBC in these principles and methods of research-based teaching. And so these two instructors agreed to cover the same material in the same amount of time with then an exam they jointly prepared, given sort of as a surprise the end of this week of classes. And so it was just probing what they'd learned from these lectures. Now, I presume you all know what happens in a lecture course. In this experimental course, it followed basically well-established method or approaches at that time, we did some modifications of this, but the students started with a short pre-class assignment to give them basic facts and terminology, so I don't have to spend class time on this. And then during class, they would be answering questions and figuring things out. And so this is an example of, they're covering electric circuits and battery and light bulbs there. And they're asked what happens to the brightness of that bulb when this switch is closed. And they're given these choices here. And each student then had to answer individually. They use clicker, which you may be familiar with nowadays. People just replace these all with cell phones, but there are a way that the students can give an individual answer, and the instructor's computer then records who they were and what answer they chose. Now, the students are not given the answer at that point. They're told they have to discuss with their neighbors. In a big lecture theater like that, that's basically the students on either side of them. And they talk about what the answer is. And after that discussion, they re-vote. And while they're having those discussions, the instructor isn't just standing waiting. They're actually circulating up and down the aisles, listening in on those conversations, getting a little snapshot of what's going on in those students' brains so they can see what's thinking like a physicist and what or thinking's not. Then there's do the demonstration, show the result. But then there's an instructor follow-up summary, and that's really based on listening in on the students, giving feedback on which of these models and thinking, reasoning was correct and which was incorrect and why. Now, I particularly emphasize that because one of the things that cognitive psychology shows us is that the place where learning takes place is really not when one thinks about something and then is told that's right. It's when you think about something incorrectly and then you have an explanation or feedback on your thinking so you're going to understand what's wrong with that, and so how you change that in the future. And so that's really was a critical part of this kind of follow-up activity. Now, that was the question I showed you is kind of a simple, basic concept question. Much of this work involved more mathematical topics, as common in physics. And in that case, students who have little worksheets, they have to write things out, but the same basic ideas hold. Now, if you think about this task, you can see how this is really giving students practice thinking like physicists. The thing I said is essential for developing their brains. They're having to decide on, in this context, a mental model of how electricity works and how it affects the brightness of light bulbs. So they have to choose the model and apply it in particular context and think of ways to test if that's right. And they're critiquing their reasoning of both, trying to defend it to others and listening to others' student ideas. And so you can see that this is really, how physicists, the basic cognitive level, how physicists spend their time. But while they're doing that, they're also getting feedback to guide and improve their thinking. They're getting it from other students, they're getting it from comparing their prediction to the demonstration, and they're getting it from the informed instructor. Okay, so that's just background on this, what happens in this kind of teaching. Remember, this was an experiment. And so both sections were given this surprise quiz. And here's the histogram of the results with, the score on the exam here, number of students here. And you can see the comparison between the two sections. There's really a profound difference here. In fact, it's a little more profound than you may realize, because just random guessing on this would give on the average students a score of 3. And so the amount of learning is really kind of how far above 3 they are. And you can see the very large difference here. That it shows you first the learning from the lecture is very small, and we have data from many others. Example, this is this, showing similar things. But I want to emphasize more the fact that you can see in the experimental section that this benefited the entire student population. So this way of teaching isn't just better for the weakest students or the strongest students. You can see the whole distribution moved up. It's just better for the students. It's how the human brain learns. Now, most of the research in classrooms has been done in introductory level courses, just because that's where more students are and it's kind of more standardized. But more recently, my group and others have been looking at applying the same ideas or same principles really in more advanced physics courses, and we see they work a lot better too at that level. And so we did this work at UBC and did a lot of studies on it. Now at Stanford, they've transformed actually most of the courses taken by the physics majors in their 2nd through 4th year. And Peter Lepage, actually, some of you may know him, he's a prominent theorist at Cornell, McGill graduate. He's actually applied these ideas teaching graduate quantum field theory and seen how it really works really well, even at that level. And all of these courses from 1st year undergraduate up through field theory have the same basic structure. And there's sort of reasons why this is kind of a natural way to do it. The students have some background preparation to give them, basic information, background. That doesn't take very long, but just saves class time. And then they're given the task to work on going through the class, and they have, in these more advanced classes, as you saw, they're smaller, they're small, intense groups, they're almost always working on worksheets because there's lots of math and justifications and things to write out. And the students, so they'll be working on those for 10 or 15 minutes while the instructor is sort of, circulating around here in the background, monitoring what's going on and answering some questions. But then periodically, regularly, the instructor will pull the whole class together, answer questions, give overall feedback, sort of pull everybody up to sort of make sure they're at the same level, talk about resynchronizing, and then the students will continue on through the worksheet, through the task for the rest of the and just repeat that cycle until the end of class. And the really two essential features that are critical in all this are the students they're spending their time thinking, practicing expert reasoning, and getting feedback on it. And they're getting feedback on that that's more effective because it's more focused on that thinking. And just as a sideline, one of the things we find that's kind of overwhelmingly, once instructors actually learn to teach this way, they always enjoy it more. And both at UBC, Colorado, and at Stanford now, we're seeing that once instructors teach this way, they virtually never go back to lecturing. So that's just an example of the kind of studies have been done. There's, many hundreds of studies have done similar sorts of things across all different science and engineering disciplines and levels, and showing that you get consistently greater learning with this kind of research-based teaching than with lectures, and lower failure and dropout rates. So, but one of this just sort of looking to the future and some recent work my group has been doing is that, if you look at these distributions, yeah, this looks great because this is much higher up here, but you still have, big differences down here that people are distributed here. And so ultimately, you'd really like to make all of these students pile up at the top, all students be successful. And I have to say, I really started focusing on this more after I got to Stanford, because as you probably know, Stanford's an extremely exclusive institution. And so students to get in there have to be really excel in a bunch of different ways. And so when I got there and I was, from large public universities saying, how can it be that we have a bunch of students, the distribution at Stanford looks just like this. There's a bunch of students down here who are doing badly, even failing. What's going on here, because they're so outstanding in so many different ways. And so spent a lot of time studying this, trying different teaching methods, found that was not enough to. And so we explored other factors that would explain what people were doing down here and what the distinction was. And we got, lots of data, doing lots of fancy multivariable regressions to untangle different factors here. And, what was the difference? Now, the first thing that the physics department had always thought was, well, it had to do with their math skills and background. We will say, no, that wasn't relevant. There's another issue about one thing they could see was their different demographic groups scored differently. And so maybe that was the factor, some sort of psychological things or something. And so, but we looked in more detail, and, first, if all you look at is how different groups, historically underrepresented minorities, or first generation college going students, or females, and you compare those with the white and Asian males in the class, you see they were underperforming. This is about half a standard deviation here. And so you think, well, maybe these are the important factors. But then we dug into this more and we looked at measures of incoming preparation, particularly incoming preparation in physics, which people hadn't really looked at before. And then when you control for those factors, you see that basically for all of these different groups, the differences go away. In other words, if you look across the entire student population, their back incoming preparation is always a very good predictor of how well they're going to do in these classes, but it's an equally good predictor for all groups of students. So there's really no gap in demographics. It's all about a gap in incoming preparation. And so, this is important because I'm sure you're in the same situation as well, really every major university, that, this introductory physics class, if you do badly in that, you really can't become a physics or most engineering discipline majors. It's a key gateway course there. And yet, the student's incoming preparation turns out to be a dominant variable in how well they actually, their chances of passing this course or not. And this is just data from Stanford, but it looks exactly the same at University of Colorado, where in the bottom of the preparation in physics, they have quite a high probability of essentially failing this course, and almost nobody does from the top preparation. And so, but this was actually, we took what measures we could of the incoming science in math and science in general and physics in specific to do this. We then created our own more targeted diagnostic tests. And this is really, really striking because it takes students about 20 or 30 minutes to do this test. It explains about half of the total variation in student grades. And most of the students who are going to fail, so what this is saying is kind of amazing. We can give a student a 30-minute test and say, we say, okay, you have a 90% chance of failing, or you have a 10% chance of failing before they've ever walked into the classroom. And I'm quite sure that your day, if you look at your own students, you're going to see something pretty similar, because we've now looked across multiple universities and we get very much the same. And so, and just emphasize that, Colorado is a large public university that lets in, almost all the students who apply there, and Stanford lets in 0.1% or something, and yet we see the same dependence on preparation. So this says it has to be something about the nature of the teaching of these courses, not the students. And I think the clear conclusion is that after looking at this, is really instructors, without really thinking, explicitly about this, they're really optimizing the coverage and the pace for essentially the top half of the preparation. But the reality is that, as we and others have looked into this, is that the top half of preparation is really determined by what kind of high school you went to, and mostly that's about the socioeconomic class of your high school. Good high schools have good, or wealthy high schools have good science teachers, particularly good physics teachers, and low income poor ones don't. And so it's really, I'll just say what the Stanford and other physics departments have long thought was a distribution of physics talent in their students was really just a distribution of educational privilege, of what educational privilege they'd had before they got into college. And then that just carried over to largely determine how they could do in introductory physics and therefore what careers they could do beyond that. Okay, so I'm going to move on to just getting into details about issues in teaching. And this is really sort of summarizing all the different things we know or the research tells us about teaching effectiveness. Now, the key idea, what really determines what students learn and how good they learn to think like physicists, is the amount they really have practicing making these physicist decisions with good feedback, timely, specific, and actionable feedback on how to improve. But there's a lot of things that have to feed in to make this whole activity or exercise effective, both up here in the features in the good design of these practice tasks, and these two down here in terms of the implementation of them in the classroom. And so, each of these boxes has a bunch of research that goes into it. And I'd argue that you include all the stuff that's represented by this slide, it really defines teaching expertise. In other words, it really defines practices that research shows that if an instructor knows about and applies these appropriate, will consistently produce and predictively produce more learning. And ultimately, we need to have these be the basis for better evaluations of teaching, but that's something in the future. So what I'm going to do is just go through a couple of these things that I think might be helpful for every teacher. Starting with, okay, what's the disciplinary expertise that goes, how does that need to go into these design of these activities? And this is a place where my own research group has been doing a lot of research in the past few years that's relevant. We've been looking at how experts in different areas of science and engineering and some medicine solve authentic problems in their field. So how good physicists go about solving important problems in their research. And we found that this problem-solving process really can be defined by a set of decisions that they make with limited information. And the thing that was really surprising to us is that it was a relatively finite number of decisions, 29 of them, and they show up in virtually every real science and engineering problem that these different experts are doing. And, I realize when you first hear that, you think it just sounds crazy. It can't be right. But then you start looking at the decisions, it makes more sense. There's some things about just deciding if a problem's interesting and worthwhile. But then there's, deciding what concepts and models are relevant to that problem. Deciding when you have information on a real world problem, there's lots of different kinds of information, and deciding what's relevant, what's irrelevant, and what's information is actually needed to solve the problem. Deciding what approximations are appropriate, simplifications, deciding on a potential solution method to pursue, deciding on priorities, bunch of others in there until getting to the end, and then having a conclusion or a solution, deciding, does it make sense, and deciding how to test it. So you can see, if you think about that, they start to sound, oh yeah, I can see how almost any problem in science, you need to do this. And you look at all the 29 of them, and they're very similar there. Now, even though all of these different scientists and engineers are having to make the same decisions, how they make the decisions is very specific to the discipline and the problem. So any given one of these requires specialized disciplinary knowledge, and so a physicist solving these, there's physics information that a physicist would use to actually guide and make that decision. And in fact, we find that their expert knowledge is really organized around to optimize helping them make these decisions. And so what that means is that to learn to think like a good physicist, that the person really has to be practicing making these kinds of decisions in an authentic problem context and practicing using the physics knowledge you want them to master and be able to apply in their future. And it's, this is really giving them the right kind of brain exercise they need to learn to develop that into a physicist's brain, if you like. Now, I just emphasize these in particular because if you think about the typical problems that you have in physics courses and exams, basically, all of these decisions have been removed from the problem. They're usually told what you can what you can ignore and, air resistance or not ignore it. You're given, the problems and exams you're given are on the, let's say the Ohm's law. And so there's no question about what you use. Well, it's an Ohm's law exam. So you use Ohm's law and so on. And so what this does in the typical course is that students learn information, but they really don't know how to use that information to do physics, if you like. And if you get back to my original puzzle about my graduate students, this is exactly what the problem was. They covered all these courses, they learned procedures and information, but not how to use that information to do physics. Okay, let me move along here I'm going to skip over prior knowledge and experience and motivation because everybody sort of gets that those are important and why. But brain constraints is something that's important and not very well known about. And so there's two critical aspects of this that really every instructor should know and most don't. And the first has to do with how the memory works. Now, it turns out sort of basic model of memory is that there's two parts to it. One is called long-term memory, and this is what most of us think of when we're referring to the term memory. It's got a large capacity and a long duration. But in addition, there's something that technically known as the short-term working memory. This is really a buffer that information has to go through before it can actually be processed and make it into long-term memory. And this short-term working memory, it has, compared to the long-term memory, it has a tiny capacity. The typical human brain can hold about 6 items, and it works on the time scale of minutes. It's really, you can think about it, it's the amount of stuff you can pay attention to at any one time. But because of this tremendous limited capacity, when you see, when the brain sees or hears some new thing, it basically pushes something else out of the short-term working memory. And so that never really gets into processing into long-term memory. And so because of this very limited capacity, any additional item actually reduces the processing and learning. And so there's a lot of things that are sort of done in the classroom setting, which is where this working memory is so critical, plays such a, or short-term memory is such a critical element, because it just means that, anything new that kind of provides some new information or something the brain's paying attention to will hurt. And so the first thing that's most dramatic in this regard is split attention. So when a student is, in the classroom looking down at their phone or they're surfing the web and while supposedly listening to a lecture, that's filling up their working memory with other stuff, and it's just a disaster with learning. and studies show it drops enormously. And the humans are very bad at actually realizing how much it's hurting. And I think when we go to teaching online, and so people have a computer screen in front of them, which, not just having the instructor talking, but all this other interesting stuff going on, it actually greatly exaggerates the damage caused by this kind of split attention. But there's also things just that the instructor can do that hurts, using new jargon terms, putting in some nice picture that has some fancy background that goes beyond the point you're trying to make, all fill up working memory and hurt. The thing that gets students and instructors most stirred up about is when I point out that studies show that any even little interesting story or joke on this actually hurts learning. And the instructors say, but that can't be right. That's the only time students pay attention to me. And students say, that can't be right. That's the only time I pay attention in class. But that's the whole point, that they're paying attention to that joke. That means they're not paying attention to the material they're supposed to be learning. And so, when you actually ask students about it, they'll be able to remember the joke, sure, but they can't remember what the class was about. And so it actually does hurt. Now, just to be a little picky, because people get so riled up about this, if the joke or story is interesting, but it really directly applies to the learning that you want, then it can be quite helpful. Now, the other brain constraint that's important here is getting in terms of how you get long-term memory, because that's really what we want, is students will remember and be able to use things later on. And it turns out one of the biggest problems of that is not getting stuff into the long-term memory. It's being able to recall it after you've learned additional stuff. And so that new stuff interferes. It makes neuron connections there. And so you try and access what you remembered, and it heads off in some other direction into the brain. And because of this, it's important to realize it doesn't work to just learn something once and then you're done. Because as you learn new things, it'll hurt. There's interference in the recall. Now, what the studies cognitive psychologists show is that you can eliminate or greatly suppress that interference by repeatedly having to recall the original material in the process of learning new stuff. It's sort of like a quantum measurement. And so it turns out that if you want long-term recall, it's much better done. You can't just do the standard practice of covering chapter one homework, chapter one exams. Okay, well, they've learned chapter one. Now I go on to chapter 2, 3, 4, etc. And basically you get to the end, they don't know chapter one as well as they did. But if you periodically, as you go through it, later material, go back and remember what was in chapter one, that actually greatly enhances the recall. And this is something that students can do perfectly well on their own without the instructor doing it. But to the extent instructors encourage us, it does help long-term recall. I'm just going to finish with very brief things about implementation. Two key things are, it's important when you're having students to work on something in class, in groups, to have very clear deliverables that students have to complete. And these really define the task and sort of structure the feedback that the instructor is giving. And then the social learning aspects of how to optimize the benefits of students working in small groups. And this is an area where I often have gotten the question of instructor can't imagine that talking to fellow students about a problem, after they've worked on it, is better than hearing their expert instructor explain it to them. But it turns out it actually is. And there's a lot of studies actually showing this. Again, it's sort of the cognitive psychology level. And what they've been showing is a very interesting phenomena, which is that when people are teaching or explaining to something to others, or even actually thinking about explaining to some others, our brains are such, this really triggers a unique sort of cognitive process that's sort of linked to social communication. And this additional cognitive processing that's triggered actually produces more learning. So it's sort of like a supercharge or extra help to the learning process. And then of course it's very useful to a teacher to hear what's going on in those student conversations, because they can be more targeted feedback. Okay, so I'm running a little over, I should stop here. Just summarize, the research shows good teaching, design, and implementation, and shows now we've got lots of research showing that we can produce better learning than a traditional lecture, and really understand in detail at the brain level why this is the case. But I'll just launch the questions and answers by asking my own question, or actually just repeating a question that I hear over and over when I've given this talk. So I might as well get it out of the way first, which is that, I give this and somebody, professor in the audience will say, well, lectures can't be as bad as you claim, because, look at all us university professors. We were taught by traditional lectures and look how great we turned out. And I just like to point out, this is exactly the same reasoning that made bloodletting the medical treatment of choice for 2,000 years, actually. And the flaw in it, just as the flaw is bloodletting, is not enough to try this on a bunch of people and some of them recover. You really have to have a proper comparison group. And that's what we're doing in these studies. And so, you professors who think you're great because after lectures, you probably would have been more successful or a better physicist, actually, you hadn't. But as long as you can't do the comparison, it's really impossible to make those claims. Okay, so I'll end here. Here's a bunch of references if you want to learn more about any of these ideas. These are books up here and more detailed resources about specific teaching practices here at UBC website, and new paper on problem solving here. And since I covered too many things for you to keep track of in your working memory, I'll make sure these slides are available that you can look at later if you'd like. So thank you.
Thank you very much, Professor Wieman. That was really, really fantastic. So just to orient everyone, we're going to have an extended half-hour Q&A session that will be recorded. And then at 4:55, we're going to kick all the professors out, and the graduate students will be invited, and other students will be invited to have an unrecorded Q&A session with Professor Wieman after that. So if you have questions, please raise your hand. Thank you, Nick. I see you. You will be first. Or you can put questions in the chat and I can read them to Professor Wieman. So let's get started. Nick, are you able to unmute?
Yep, it worked. Thanks, Carl. That was a super fascinating lecture. So I have the anti-correlation between preparation and then the subsequent performance of students is very worrisome. So what are good solutions to this? I mean, do like boot camps work, or somehow easing students in for the first year, or like how can you work to try and tighten that distribution?
I wish I knew. We're studying that and we've tried a bunch of different things. Boot camps don't, at least we have limited data, but boot camps don't seem to work. They're just not, I mean, you kind of have to look at, we're talking about intro physics, and as we've probed these students' preparation, it really, the difference, and I'm sure it's pretty much the same for your students, it ranges, there's sort of, a really privileged student will have 2 years of physics, basically. And there's a unusually, what's kind of unique about these first year courses is the large overlap in content, and especially in physics, but also in chemistry, between what they get in a good high school course and what's actually in a college course. And so, a well-prepared student, they'll have essentially 2 years of that stuff. A really poorly prepared student, and these poorly prepared students, it's been interesting. They've taken, in many cases, especially the ones who get in STEM, they've taken physics courses, but then we look at what they've learned from those, and you say, how could they have taken a physics course? Well, we start talking to them about what their physics teacher was like and what they were doing in those courses, and we're going, boy, that's just not teaching physics. The person didn't know any physics. So this is a long way of saying boot camp just aren't enough, is what I concluded. And when we tried a lot of supplemental instruction sort of things to help them out, and it just wasn't enough. And so we think, and we've started to do, we have some preliminary kind of evidence of this, but I'm not willing to make any definitive claims, but we really think, look, we have to really make a course that essentially cover, a different course. And then we're sort of trying to build a ladder. And so, in other words, and had pretty clear that sort of having it's sort of a remedial course, but it's not a remedial course in that you take this course, the regular course, or you take this one, and it's supposed to be, we're thinking about having them go through a specific class course like this, that then they would then, so they will have to spend an extra term on this, but then it feeds into the regular one. So that's one alternative. The other one that's actually worked, but we have very limited data and a limited circumstance, is that we decided, let's see if we can create a new introductory physics course that gets these students prepared for at least engineering careers, but doesn't have overlap with a lot the material they would have had in high school. And so we've developed and are in the process of trying to get this published, but I can send you a course that really focuses on problem solving and focuses on these real world problem solving decisions, which we have some indication kind of leave them better prepared to go on into engineering, but looks, a lot of the same topics are in there. There's fewer of the same topics, but we've really tried to focus on topics that are really important for going into engineering, and then give them these kind of unique problem solving skills of the kinds I looked at. So they're doing much more real world, realistic problems that prepare them. And we find those courses aren't nearly as sensitive to incoming preparation. So that's good. How well these students succeed after taking that is, we don't have as much data as I'd like before I can claim anything. So, but the main answer is it's a really, I think, a critical issue now that we have to be thinking about, of how we're disadvantaging these students who come from poor high schools and making it so they have they're very limited in what they can do in college. So we just have to, and we don't have I can give you great solutions to lots of other problems where we know it better. That one we don't have yet.
Great. Thank you. Jim, do you want to go ahead? Jim, are you able to unmute? If not, I'm going to read your question.
Jim the cat.
Yeah, I'll read his question. He wrote it in
Okay.
the chat. So his question was, do you find resistance to working in groups? For example, students not wanting to interact within their small groups, parentheses, I do.
Yeah. So this is a very good question. And so there's a few things or a number of things we've learned about just studying this and how to do it better. And so how you grade is critical. You know, if you're grading on a curve where that means students' grades are not determined by what they learned, it's determined by how much better they are than the other students in the class, that really hurts people working in groups, because obviously collaborating so somebody else learns something hurts your grade. So you have to make the grading so that it's measuring how well they learn the stuff, not in comparison. But more than that is you really have to start out by setting out very clearly and explicitly, and I have run through this little exercise. We have it described on the CWSEI website of sort of norms of behavior and ways to make the group collaboration effective. And, you know, the reality is that there's very few people who don't kind of, you know, work effect or see value in working with other people, but you have to structure it so that it's kind of clear how they have to do to behave in that way. Now, so if you do that right, then and set that up right, then there's almost all this, or I won't say almost, a great majority of the students will see this as a profitable, you know, collaborating at a profitable activity. There are a few that won't in the typical class, and one can, you know, deal with that partly by just as a good instructor, you kind of monitor how these groups are working and you intervene a little bit when there's troublesome group members, and sometimes in unusual circumstances, you have to rearrange groups. But then and so if you do that, you know, now you're down to 5 or 10%, I would say, maximum, who are actually resistant to it. And you know, at some level, I just figure, okay, don't worry about them. You can make it clear to them that and they can go off and work on themselves. But the other thing that's really, actually, I should have said at the beginning, that's most critical is you need to make the problems hard enough that they can only do them usually working in groups, that they really need the benefit of sort of multiple minds working on it. That's valuable, both helps them collaborate with groups, but it also means they learn more because they're doing harder problems and thinking about them better. So, you know, putting these things together, you end up with a very small fraction, but it's not zero. And, you know, basically you can kind of, at least I've taken as, all right, it's their funeral at some level, you know, we know they need to learn to work with people in their future careers. You can tell them that. If they're going to not do it, well, that they just have to, you know, at some level you can ignore it. But I think if you follow those other steps about optimizing it, that makes it a very, you're dealing with a very small fraction. The great majority actually are quite happy working in groups. And one of the measures of that is that there's this question about how often you should should you rearrange the groups or not? And there's arguments either way, and I've come to just say, okay, I go halfway through the class or halfway through the term, and then I let them vote on whether they want to rearrange groups. And now what we see is just overwhelmingly, 90% of them will say no, they want to keep in their same groups. And that's just a statement that they, are seeing this effective and they want to and working with the people we've got them into groups with.
Great. So there's a couple of questions from the chat that I'll read out. So Tim Merritt asks, does getting students to teach other students in turn help their own learning? I think you alluded to this in your talk, but maybe you have a bit more information about that.
No, I mean, that's it. It's basically, yeah, thinking about teaching, and but teaching is really, it doesn't have to be so explicit. It's really thinking about explaining something to somebody else, and even kind of thinking about their explanations. It's so the more when you just shift people from thinking about, okay, I'm going to try and understand this, make sense of this physics idea, and you give them a task of, okay, you've got to try and explain this to somebody else. That just turns on the brain in a different way. That's quite, very demonstrably effective at helping their learning. And so, like I say, it's sort of most natural and helps the most in working in groups with other students. But you can just sometimes you can give students a question of, think how you'd explain this to a younger sibling, and that actually has them think about it again in a similar sort of way. So that's just emphasizing how this kind of teaching or explaining to others helps one learn. And everybody who's taught sort of knows this, right? You teach a subject, you always think of how much better you understand it afterwards.
Thanks. We have another question from John Manuel, who's following up on Nick's question to ask, how much of this research-based teaching and active learning is being moved down into the high schools?
I don't know about that, so I can't answer it.
Fair enough. I have a question of my own, which is, oh, I'm sorry. Go ahead, Samuel. If you can you unmute yourself?
Yeah, I didn't mean to stop you as soon as you talked, but anyway, so I've taken a few classes at McGill that were taught with sort of the new model, and I guess just as a student, it seems like there's a bit of a trade-off you have to make when you design a course where you have just pure delivery of material and time set aside for students to work on a deliverable in class. So how do you design a course where you're certain that you're delivering enough material appropriately, but also that students, have the time to work with each other and produce something and really learn the stuff?
Yeah, so I mean, there's two parts to that question, and I'm glad you asked, because this comes up really all the time when people are starting to try and teach this way is, how do I cover enough material? And so there's two, like I said, there's two parts. The first part is, the goal of a course is not covering material, it's the students learning material. And our research shows those are vastly different things. And I'll point to chemistry actually, because they're the most blatant ones, where introductory chemistry covers what even the people teaching it say is way too much material, but they feel they have to because that's the way this course is taught. And students come away, learning just a tiny fraction of it. So it's a remarkably silly exercise. Having said that, and getting into physics where we're not so crazy, but probably still are covering too much material in many courses, is that we've, in developing these methods and studying them, we've actually thought very carefully and figured out principles of how to optimize how much material you cover, as well as optimizing how much material students learn. And we actually find in most physics courses, if you design it really carefully and most efficiently, you can cover just about as much material. Often, I would say in the majority of cases, it's maybe a little less, 10% or so. But there's also actually a number of of cases where people, particularly in more advanced courses, find they're actually covering more material. And that's showing up. And the reason that can happen is a couple of different ways. One is what you're doing in class is giving students greater capabilities to figure things out on their own. So you can actually have them, cover material on the homework, for example, without having to talk about it in class because they have the tools in class to go and work it out on their own. So that's one way you can magnify the amount of coverage. The other way is there's a lot of things done in class. For example, a frequent thing is derivations. And those are, sitting there watching somebody write on a blackboard doing a derivation is just of no learning value whatsoever. And so, for example, taking that long derivation and having students do some worksheet where they have to kind of complete critical steps in, the critical thinking steps in that derivation. Now they actually learn much more from that, but it actually takes them less class time to do it. And so you really, if you do things efficiently, what we find is you really don't have to give up much coverage. But
Okay.
it does, it does require kind of careful thought on how to maximize.
Thank you. Yeah, that's perfect. And I just want to say that I enjoyed these courses at McGill. I thought they were my favorite physics courses because I know my professors are in here, so I don't want to rustle any feathers. But no, it's a great method.
Great. I think Christopher, you're next. You can unmute yourself.
For sure. So thank you again for the talk, and thank you also for the time that goes into studying, teaching. Aside from all the physics that you do, I'd like to ask a little bit more about this idea of preparation. First, because I find it cripplingly, depressingly saddening that that's the primary predictive measure, and I also note that from the talk you said that it's math SAT or ACT scores or concept inventory scores that are the primary predictive tools. But I mean, can you unpack that a little bit? What goes into the idea of preparation? It couldn't just be facts, right? Because the facts are measured by concept inventory and SATs.
Yeah, so first I want to emphasize that those are not necessarily the best measures of prior preparation. Those are the measures we could get of prior preparation. Okay, so that's in some ways, that's the most horrifying part of the result, is these are pretty crude measures, and yet they're say so much. So, but let me go into more detail. First, this part of the thing is probably unique to Stanford. Other places it could very well be different. But so in Canada, you don't have the math SATs, and so, but I'll tell you, this is a standard test of sort of math skills that you have to take to apply to almost every college and they decide to let you in based on those scores. Okay, well, at Stanford, those scores are universally quite high, and so we see that actually the math needed in the intro physics course, all the students already know that. And so what that math SAT test is doing, we believe, is just general math and science preparation more broadly rather than any particular math topics. And so that's our interpretation of that. And then in terms of the physics knowledge, I mean, the physics concept test is a pretty useful thing of probing particular concepts, but we tried to improve on this by making our own diagnostic exam then, and that's actually published now in the physical education research APS journal. And so there we picked out a number so we have a few of the physics concept questions, what happens going up hills and so on. But we also have a few things that we knew were particularly critical, like vectors and understanding how to add vectors and resolve them, and several other pretty basic ideas in physics and math, or math as applied in the physics context, that we sort of, from teaching these and instructors who teach them, sort of identified as problematic issues. And so, that's what we've got. And that diagnostic is then pretty short and all by itself quite predictive. So, but again, you can think of a lot of things it's not covering. And I'm afraid that if we had really good measures of preparation, we'd be able to tell a student what grade they were going to, get before they ever started a class. I mean, it's really scary how strongly predictive these things are. So, I mean, I don't know if that answers your question, but that's, the
Well,
basic.
it does answer a little bit, but I think I'm more wondering is what else do these metrics capture? So do they capture emotional intelligence, perhaps? Like, do they
No,
capture
so
grit or something like that?
yeah, so we don't capture any of those things, okay? And yet, there's these things people look at: emotional intelligence, grit, time management skills, social interactions, how well they can get together and collaborate. All these things that, if you'd asked me, I would have said were pretty important in how successful students are. We don't capture any of those, and yet we can still tell you who's going to fail and not fail with a very high degree of accuracy. So so I would say that's what's really striking and revealing about it, is that it's not, there's an awful lot of things people thought were important that don't seem to be all that important in introductory physics.
Okay, thanks.
Great. So Eve, would you like to ask your question?
Okay, I think I can unmute. Awesome. Okay. All right. Thanks. First of all, thank you, Carl, for the really nice talk. And I really liked your emphasis on teaching the students how to be a physicist, and your emphasis on the decision-making process. So in my, I guess, somewhat limited experience, because I'm relatively new faculty member here, whenever I assign students questions that were like really well defined in a way, as you say, like we really take away all those decision-making process in this typical problems, versus the questions where it was more open-ended, where I explicitly expect the students to, make their own decisions, try to come up with their own reasoning to make certain approximations. Do they make sense? But what I noticed was that I have a lot of pushback whenever I assign the latter type of questions. And furthermore, I do notice a significant gap between the different students who are more self-assured. They just have this confidence, versus students who are less self-assured. So I'm wondering how we can close that gap a bit, and whether there's a better way to prime the students.
Yeah, so, giving students that kind of problem is, I mean, it's so radically different from what they've ever seen before, that you really have to appreciate that how it's kind of completely changing the rules on them of what they think a physics problem should be and an answer to a physics problem should be. And I mean, I'm not sure, you mentioned you see a big difference in the student confidence, how they deal with them. I actually see something slightly different. The ones at Stanford who have kind of done the best in physics before, they're the most deeply ingrained in how they think a physics question should be answered, and they're the ones who are kind of the most outraged that gee, I have to go find information to solve this problem. I have to think how fast I actually can run in order to answer this. What a terrible thing to give me as a physics problem. And so one has to really recognize these kind of student preconceptions and sort of bring it in gently, I guess is the way I would say, of recognizing that it's just a radical departure. And so you kind of try and bring it in, slowly in pieces. But the other thing to do is always keep emphasizing to them, and this is fairly easy, is, you look at the traditional physics problem, nobody would care about the answer to that. You got a pulley on a frictionless ramp, who besides a physics teacher would ever think that was worthwhile knowing the answer to? And so, you can make the point, the kind of problems you bring in or something, oh, there's a real reason that somebody would need to know this, how to make a bridge strong enough, or, protect a car from killing how to design a car to keep from killing the passengers if it ran into a wall. And, but, sort of conveying, you're teaching them how to do useful things as opposed to artificial physics problems, but also just, helping them get in gradually in little pieces that they can deal with. Because otherwise, yeah, it's just a scary sudden change that for them, they thought they know the rules on how to be successful, and suddenly you're telling them no, they got to do some completely different kind of thinking.
Thank you.
All right, I think we have maybe time for one last short question, and my apologies to everyone who's asked questions in the chat. I've been trying to go in order of who raised their hands when. So Matt, I think you have the last question here.
Thanks. So throughout this discussion, there's been the thread that the historic system of lecturing isn't up to snuff. And part of that historic system, at least at research-intensive universities, is to put our star researchers forward in front of the classroom and ask them to deliver these lectures. Your research about success being proportional to preparation, and especially the demonstration of the junior person versus the seasoned lecturer, must call into question not just the traditional lecturing approach, but also the tradition in universities like ours, where we insist that people be both star researchers and lecturers. Should universities also be questioning that and focusing on the preparation and having experts in the classroom instead of both?
So I think you still need both, and this actually gets to be a whole variety of factors come into this. But the first thing we need to change is just the idea of teaching expertise. And right now, teaching really isn't thought of as an expertise, that in universities, it's kind of, oh, well, you go in and you can teach or you can't teach. And it's kind of what best for any instructor is what they kind of prefer individually. And what the research says is no, that's just wrong. There really is expertise in teaching. There's things that if you do it this way, they're going to be better, and it's so.
It's exactly like your summary of students, I guess.
Yeah.
That you're not born a good lecturer, not born a good student. You're taught.
Yeah. And there's a bunch of things you need to learn to be a reasonably competent expert teacher, I would say. Now, it doesn't take as many thousands of hours as it does to be a good physicist, because the standards are quite a bit lower, but it does take reasonable time to learn. And the real indication of the lack of appreciation for this is the fact that no university actually tracks what teaching methods are being used in its courses, even though we have good evidence showing some are a whole lot more effective. So, it's as if we had, hospitals filled with doctors, and you'd go in and maybe some of them would give you antibiotics, and some would give you bloodletting, and some would give you magic incense. And the hospital says, well, it's whatever they feel like doing is appropriate. So that's the first thing, is we really have to have, start measuring what's being used and evaluate and reward people according to using the practices that get the best student outcomes. Now, but the issue of, should we not have people who are experts in research involved? If you get back to my picture with all those little boxes on them, that one box saying disciplinary expertise, you really have to have respectable level of expertise in the discipline to kind of appreciate what thinking in the discipline is at a high level. And so, teaching introductory physics, sure, you don't have to, you could have people who know a modest amount of physics and are expert teachers, but you get above that at all, even, I see things in E&M, and certainly starting in quantum mechanics, you really are going to be very hard pressed to have people who have the depth of mastery of what thinking like a physicist is, to be able to have the right practice and feedback in that thinking. So I think, in fact, this kind of research in some ways is the best justification of the research university. We have, in some sense, that it does show how expertise in the discipline is kind of critically important. And getting back to the question about high schools, in fact, the one thing I do know about high schools is that, and a little bit lower grade levels, is one of the critical problems of those instructors teaching using these methods is you just have to know the subject a lot better, because if you're lecturing, you're basically, you can stand up there and repeat what's in the textbook pretty much. And it's just this, it doesn't matter if you are just repeating the textbook or if you actually understand what's in the textbook, you're conveying the same. When you're having students thinking about these subjects and you're giving them feedback and designing activities for them, you have to know the subject much better. And so that's a real problem in the K-12 system, of the teachers knowing the science well enough.
Great. Well, thank you so much, Professor Wieman, for a really fantastic talk. Let's all take the opportunity to, again, virtually thank him for sharing his time with us.